birthdays on the
Some important TypeScript problems, yeah, but not very
22 plus
wordish.
4 is 26.
I don't know. They're not like
26.
Okay, so this is growth and decay. You probably have seen stuff like this in pre-calc. If you've taken a pre-calc course, there's talk of radioactive decay, but you're kind of just fudging it and not really doing like the full-blown version. So this is the full-blown version of that. So the first thing that we're going to see in 6.2 is the AP's only requirement for differential equations, basically. What's the only method they require you to know for differential equations? And that's solving differential equations, because in the last section, they just gave you the solution, right? AP is only going to require you to know one solution method, and it's solving differential equations by what's called separating variables. Which is a really simplistic solution method. Things that drove me crazy is even in ODE 1 and PDE 1 in college, we focused on this basically the same technique, just extended a little higher for so long, and I got so bored. So I hope that doesn't happen to you. Okay? So separating variables. I was just going to demonstrate. So let's say we have this differential equation. Pretty simple one. So what do I want to do with that? I'm going to show it kind of very specifically this first time, and then in the future we'll go through it a lot faster. Okay? So separating variables means get your y's on one side, and get your x's on the other side.
So where y prime equals...
So times y, exactly. So you multiply y up to the other side, you get y prime y equals 2x.
So then you have...
Now, let's think about this. What's another way to write y prime?
dy dx.
It's probably a better way to write it. Leibniz really had something when he was thinking about the notation that way. dy dx, right? So now what we're going to do is we're going to, once your variables are separated, step 2 is just integrate both sides of the equation. Let's just operate on both sides, right? That's the Old Testament rule of algebra.
Well, the
Except now I'm using the integral.
So
of dy dx is just y.
Now, what's missing notationally when I put that
the
integral there?
dx.
The dx,
So
right? What am I
dx.
integrating with respect to? And we're pretty much always integrating or differentiating in this class with respect to x. What happens over here, do you guys notice?
The x is dx is crossed out, so it's...
The dx is cross out, and you get the
Y
integral of y dy equals the integral, you can bring the 2 out if you like, of x dx.
I thought those canceled.
What canceled?
When you take the integral of the derivative, I thought they would just go away. Both of them, like the dy and the dx.
Well, this isn't the derivative. This is I wrote it in green because it's like it's part of this integral notation. It's like
No,
when you put this there, you gotta put
no.
that there.
The dy dx.
Right.
And then
then
the integral.
This that we put there canceled out with that. So what's left is dy. But see, this dy needs to be here for you to actually perform an integral now. If there were two a dx and a dy, you'd be like, strange, I've moved to Calc 3 land and I don't even know what that means. Okay. So I think it kind of does make sense when you go through it with this notation. So if you need to look at that notation a little more carefully, you can read the book. But I think it makes pretty good sense. Anyway, what's the integral of y?
y squared over 2.
Y squared over 2. Plus a constant, right?
Plus c.
So I'm going to write, I'm not even going to write it down, but there's technically a constant there, right? When I do this one over here, I get 2 times
X
squared over 2.
X
The
squared.
2's cancel, right? You get x squared plus a constant. So what I'm going to do is think about the constant on this side and the constant on that side. Since they're just arbitrary constants anyway, can't I
make them the
just
same
move this
thing?
one over here and absorb them together?
So
plus
then you have
C1
plus c.
Exactly. And I'm going to call this, books call it different things. This is my recipe. I'm going to call it CT. Your book might call it C1 or something. I'm going to call it CT, and my T stands for temporary. Okay? My T means temporary because that's only the temporary constant y, have we completely solved for y? Have we found, remember, when you're solving a differential equation, the goal is to find the function f of x, or y. Is that solved for y yet?
No.
The good thing is we've got a y. All we've got to do is
Root
do
x
some algebra
squared
and
minus CT.
moving around.
Minus 2.
Right, so you multiply by 2, so you get y squared equals
Oh, that's
2x squared plus 2ct. Can't you just absorb these together too, since it's just an arbitrary constant? Yep. So then y equals
square root of that.
just square root, plus or minus. And then I'm going to finally just call this my
C1.
resulting constant. What you call it's really up to you. I want this to be CT for its temporary, and then this is the final constant that's after it's absorbed all of its different parts, okay? You're going to absorb all those different temporary things into one constant at the end. That's why I like CT. Okay, that's separation by variables, notice. Not super hard, right? There could be some trickier problems, but it's not too bad. What else might I want to do now? What if you had a condition? Because what kind of solution is this right here?
That's just a general.
It's a general solution,
So
isn't it?
then they give you your condition for C equals whatever.
Right, so let's say they gave us a condition, and I see like 0, 4. I'm using your desk if you don't mind, Caitlin. So now I'm going to just plug in and find the particular solution. So I go 4 equals plus or minus square root of 2, 0 squared plus c.
So 4 squared, 16
4 squared, 16.
equals C.
So I think we really have two particular solutions because of the plus or minus thing here, right? So our two particular solutions are y is plus or minus the square root of 2x squared plus 16. So there's one, there's the other. Those would both satisfy the equation. So if you take either one of those, you plug it back into the differential equation, it should work. Okay? Can you guys see it working? If you take the derivative of this, isn't it like 1 over 2 square root, blah, 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 chain rule? Can you see why like one is over the other here maybe? I think it's going to work.
Times, yeah.
Just think about it a little bit. Okay, should we see another one? So no exponential growth or decay yet, but
Mondays suck though.
okay.
And I want to score. Really, every time
Nobody cares about the fall.
Okay, let's try this one.
Nobody cares about the fall.
Okay, so all kinds of applications in science. So a plethora of applications.
That's a nasty word.
It is pretty interesting. It's kind of gruesome though.
Involve this kind of scenario. So they have the changing variable, thing that's changing, and it turns out in a lot of cases that changing variable is proportional to itself. And this is where a lot of differential equations come in, okay? So, in other words, for instance, the rate of change, dy dx, rate of change of y, changing with respect to x, I might say in a lot of situations, the most common one is that it's directly proportional to y. Yeah? In like algebra 2, we talked about things where directly proportional, but did we ever put y here? I think usually
So
we had
K
like
stands
y equals
for-
k times x. K is the constant of proportionality here, right?
And that
So
means-
remember in algebra, this is the derivative of y is directly proportional with y, and a constant of proportionality is always there. If I said the derivative of y is indirectly proportional
Y,
with
okay.
x, what would it be? I'd say
Wait. Oh, indirectly.
derivative
K
is
K over Y.
k over, and I said x.
You said X.
But indirectly means division, directly means multiplication for proportionality, if you remember. What does jointly mean?
Both.
Isn't there a J?
Jointly means like multiplication.
This looks like Q.
If it says joint, it's going to be like all multiplication. So I could say that the derivative varies jointly with y and the cube of x. Things like that. Remember how to write that down because you're going to start to see some problems like that. Okay.
I don't still understand the proportion, but whatever. We'll wait to be there.
I have an Algebra 2 video you can watch if you want to look at it again. Anyway, a lot of things end up having some kind of constant of proportionality and a y in here. Might be divide, might be multiply, but the y is what's new. Usually this had to be x before, we couldn't have dealt with it. Okay, so how would you solve that differential equation? This is like one of the most, pretty much the most common differential equation in the history of the world. Let's solve it with separation of variables and see what's the most common solution ever.
It's going to be
You guys dying from the heat?
KX.
Yeah.
It's hot, huh? Okay, so what should I do first?
Move
How
them
many-
over. D over D.
Separate variables, right? dx should go over here, y should go over there. So I'm going to write dy divided by y equals k dx. Going to integrate on both sides. I don't really need to add any extra things because they're already there. And if I write this like this to help you remember, what's the integral of that?
Absolute value y.
This one is the natural log equals kx.
Where did the
That's natural log, that's kx. Both of them had a c. We'll absorb it to this side and call it the temporary c. Okay. What's up?
Raise them to e.
Oh.
So then it's E. Yeah, and look at it.
I still don't. Where'd your x come from? The kx.
What's the integral of 1?
It's x. Okay, so that's what you're doing.
Yep. Solve for y. What do I need to do?
Raise the natural log to e.
E it.
Yep.
Can I put it through on both these?
Uh-huh.
Not unless you're
No.
careful. So you really just get y here. Equals e to the kx plus a constant. Now technically, if you're going to split that up, you can go e to the kx times e to the ct. This is
That's
just a
the
constant,
constant.
isn't it? So we'll call that c. So if this whole thing right here is just a number, let's just call that the number c.
So which way? What if you left it like the one above it?
You can't.
Okay.
You need to know how to do this. You'll see very clearly why that is when we get to our last differential equation thing. Yeah,
That
then we
really
rearrange it.
And is that because of the kind of cyclical nature of?
Yes. We're going to use this cyclical nature to do a lot. I said I was going to show you a little bit more differential equations than they do usually. So this is big. This is the most common solution to a differential equation. You have e to the x and some constant in front and some constant up there. So if I wanted to know like this, if I wanted to know the particular solution, how many conditions would they need to give me?
No.
How many conditions would I need to find the particular solution? I need one condition to find
C,
this,
and one for.
and I need another condition to find that.
Two.
So I need 2 conditions really to get this. One for the constant of proportionality. I could have done that at the beginning if I wanted to. And then one for this constant from the differential equation. Okay? So that's the kind of thing that you have exponential growth and decay with, right? So maybe let's do one question like that today and then we'll leave the rest. So let's see. Yeah, let's just do this one.
I was really tired yesterday. I felt bad because we were sitting in the front row. So I usually just
So let's say we've got a radioactive decay problem that says this.
felt like a horrible person.
Suppose 10 grams of isotope Pu-239.
Pluton.
That's plutonium, yes. Certain isotope of plutonium anyway, are released during the Chernobyl accident.
Conspiracy.
I'm not sure if this is actually true, but Chernobyl was a big problem.
It was really stupid how they handled it.
Those darn Russians.
Too prideful.
So notice, in pre-calc, we did this kind of thing. We just did it the cheating way. Okay? So if you note here, the differential equation which describes this situation, the reason the thing worked the way it did in pre-calc, and we even did it a more cheating way in pre-calc, but is that the rate with which y is decaying is proportional to y itself. And what do you think k is going to be for this one since it's decay? Is it positive or negative? K should turn out to be negative so that you get an exponential decay function. We know from what we just did that the solution to this differential equation is what?
What we just had.
C e to the kt.
Oh, yeah.
Why?
And k is going to be negative, so you get a nice decay curve. So that's the way it
How did you know that
works
this
like
one was directly proportional?
Well, they didn't really even tell me. There's going to be some problems that'll say blah is blah proportional to whatever. Write that down and then solve from there. We'll do one like that tomorrow. Okay, I just wanted to do one like this today, so give us a shot if you want to start. So, I'm not going to go through that process again and solve this. It's the same thing. What's the solution? The solution is y equals...
C E to the K.
This we called like the decay or growth rate before, right?
Changing.
C, does anybody remember from back then? What did we call C? C was a constant, yes, but how did it affect the scenario
Was that
here?
the half-life right there or whatever? No.
Was
Was it the 10 grams?
It was how much you started with, yeah. That was the initial amount, okay? But basically, you don't even need to know that if you know some differential equations. You just say, start plugging in and figure out what I need to figure out. So you say, okay, plug in some stuff. I know that I have 10 grams.
Don't you want it to equal 1, so you put 1 in for y?
I'm going to do that, yes. But first, I think I need to find something else, yes.
You need to find K.
Okay.
So I need to find k first. So how can I help that?
So 1 equals 10 E K T. Solve for K.
Okay, let's try that. So if we start with 10, we get 1, e to the k. What's your t?
Oh wait,
We don't
we
have
still
T.
Yeah.
Oh, okay.
Is it 230? No, that's
So-
just the number of.
That's not going to help, right? Because we don't know how long t is. Isn't that what we're trying to find?
Mm-hmm.
Good guesses, though. What else do we use? Just something to do with half-life.
Is T like 1 over y? Because it's half of y?
Would we find out what the half-life of that is?
Or
Yeah, maybe we should.
1
Google it.
half y?
I'm sure you know on the paper.
It's good ideas, though.
No.
The half-life, in whatever the half-life is, how much of it do you have left?
At 1 gram though. You know.
0.5.
So is it 0.5?
0.5.
How much of this do you have left? Not this is what we're talking about later. If we're talking this,
5.
there's going to be 5 left if we start with 10, e to the k, and then we just don't know how long it takes for that to happen, which, Austin, how would we find that?
Google it.
We could Google it, right? Exactly. So you'd find the half-life. Now remember, the half-life is going to depend on the substance. So you'd Google Pu-239 and see what's the half-life.
So do we need to do that right
Or do you have it?
I have this one.
So wait,
But if you need to, you might have to.
so you
On the
start with
AP
5
test. Google.
Pull out.
because that is the
Okay,
half-life?
Yeah, so you look it up. That half-life is that long, but do you guys understand how this works? I mean, it's not that bad. So then you solve for k and you go, okay, what else? What do I do? Help me solve
You
for k.
move 10 over.
Move the
And then
10
you take
over.
the natural log.
So I get 1/2.
So natural. 1/2
Natural log of 1/2.
equals k of 24.
Natural log cancels e, so you get k times 24,000.
So then k equals natural log of 1/2 over 24,000.
Is that 24,100?
Yes.
Yeah, I'm just not saying all of it.
And then you write what that is. Make sure you keep all the decimal places in your calculator. So I might write this down, approximated. What is that?
Natural log of
But I want to keep it in my calculator and keep it totally stored in my calculator so I don't lose accuracy.
How do you
here.
store it again?
Just leave it like on your screen and then go and copy and paste it.
That is
How do you do that?
negative
Scroll through your calculator and go
2.87
grab it.
blah 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 times e to the negative 6.
What is it?
Negative 2.876 times the e
No,
to the
it's-
negative 6. So it's negative.
K equals negative.
Okay, so it gives you it in scientific notation.
2.
Why don't you just put the times e to the negative 6 though? Because you know that it's what it's gonna
I got you to the negative.
be.
I got eaten the negative 5 as
So
well.
if I said alpha A.
Okay, so lesson here, guys. When this gives you scientific notation, you need to write it down like this. I think that would be much better. So it's e to the negative 5th. That means 4 zeros,
0, 0, 0.
and then
2, 8, 8, 8.
fine. But we'll write it down like that for our equations that we're writing. But we'll keep it stored in our calculator all the way if we can.
Where should we store it? This one?
You just leave it on your.
I just leave it on your screen, honestly, and go paste it.
So then now do we go
You can
put it
store
back
in
in
a
the?
variable? Yeah.
That
So do we
was
put it
my-
back in the original with the K and T?
Yeah, so this is the initial amount, e to the negative 1, 2, 3, 4, 288t. There's our
So
new
wait,
model.
that was K, but do you have to multiply it by T? It's like you have
Yeah.
KT up there, so it should be that. Oh, okay, but are you gonna, is T
Well, have I
still
answered that
24?
question yet? Yeah, I found the constant.
And so then you know that y is 1 in that case.
It's just going to be the same calculation again, isn't it? It's just
One-
now you know that.
now
So
you're
you go 1.
10e to the that t. You do it all over again.
And isn't the, even though we have this now instead of that, it's just going to be the same kind of thing. So tell me what t is, approximately.
I thought we already knew
See if you
T.
can come up with the same t as
No,
me.
we know K.
No, but like,
Yeah.
why don't you just use the
We
half-life?
knew t for the half-life. You're telling me that it's going to take 24,000 years for 10 to become 1?
No, that's, okay, so it's just
It took
for it to become
24,000
5.
years for it to become 5.
Okay.
We want to know how long it takes to become 1.
So T is like the time.
Yeah.
Oh.
Yeah. But the calculations, like, you're like doing the same thing twice almost. Can be pretty quick. What do we get? How many years? Do it. Calculators. Make sure you can do it.
Yes.
But you're probably right.
I got like 79,950.87.
That's what I got too.
Anybody have something else?
I got
Second.
80058.46. So I didn't get that.
Remember, on the AP, what are they going to take?
I got.
One answer.
So, yep.
Rounded to 3 decimal places.
I got.
Now, they might say sometimes, like, what is it to the nearest year? And to the
I got
nearest year, this is
900.
the answer.
79951. Oh, no.
79,726. Is that it?
No.
Darn it.
Did you round?
That is... If you had 5.8, I might have taken that. I'd have to look at it. That's
How
what I
did we
got.
get something?
It's because you're not using... You're using this instead of the actual full thing.
See, but I didn't.
So
Did you
you
not?
store it as
No.
A, and then like divide, okay, by
Yeah.
A.
See if you can get closer. Try it one more time.
I need to get that other answer.
What's this right here?
Okay, so.
See if you can get closer at least.
So,
What are we storing this as?
You don't have to store it.
I was just gonna store this.
You can store
If
it
you
as...
store it seems like it'd be easier.
Oh, I got it.
I don't think that they would
Yeah,
ask you
I'm
something
still-
like this that wasn't on multiple choice. But
So, L and.
I'm still not getting that.
Why don't you put it in using alpha at this time instead, and then just make the entire
I did
equation?
do that.
Cause see, then I'm
Yeah, I
doing-
did do that.
Watch.
Divided by.
I went like that. Okay. Yeah.
Oh, I got that.
Now I'm gonna go.
I'm getting 8005.
natural log of 110
Yeah, I got
Oh, I
5.8.
got that. Yay.
divided by.
Austin Air 5.
I got
Maybe just
5.
leave
I
it.
got 5.8.
You get 58.46.
But then
So
it's
maybe it's
58.5.
58.46. Yeah.
And then if you round up.
Eh.
Holy cow.
I think we're fine. So if you got 58.46 there, we're good.
This is for you.
See, but why wasn't it doing that when I used alpha y equals?
I'll tell you in a second. I don't know. Let me look at
Hey,
it.
dog.
Because I was, like, I put it in the same as you did.
Good question. I want to see what you did. Okay, so I'll do another example or two tomorrow.
Oh no, I see what I did. I put in 24,000, not 24,100.
Oh, that's just sneaky.
That little one, right?
Is that the assignment?
What does that mean?
Yeah.
That will make a
Time to go do
difference.
some crystal
You can put
math.
it back.
Mathematics about crystalline properties.
I actually have that.
Like that, and you just spend hours trying to figure out what you did wrong. It's like, oh, I went 1 instead of.
You guys are so loud. Riley.
I dropped all of
How
my
did you
things,
do?
and now I have to go grab them.
Okay, here we go. So, this, I went back and picked up a couple more slope fields from our arc functions.
Yay!
They're kind of neat.
That was
These ones,
sarcastic.
let's make both this parts due Wednesday. So, I'll show you a couple more examples
Choking.
tomorrow.
I almost died there.
Yeah, let's go Wednesday.
We cut it. My Far Cry 3 times just getting smaller.